Okay guys, welcome back. We are now moving into our next topic, which is the last topic of our general routing discussion. We are going to be talking about GRE and IP in IP tunneling. All right, what we're not going to be talking about in this particular lesson is DMVPN and multi-point GRE, IPsec with GRE, and so on. Our focus primarily is just to kind of introduce you guys to the concept of tunnel interfaces and specifically what is GRE and what is IP and IP, which is basically the same thing as GRE, but we can only support IP passenger protocol. All right, so we're going to talk about GRE tunneling in this case. We're going to use this topology here to kind of build out our GRE configuration. We're also going to wrap up the lesson by talking about IP and IP tunnels, and then we'll also talk about the concept of route recursion and tunnel errors and lookup errors that might happen with tunnel configurations. This is a little bit of a precursor discussion to what we might actually see, well, what we will actually see later on when we talk about DMVPN and tunneling techniques with DMVPN. That's going to be a completely different lesson. All right. Now, with regard to GRE, GRE is an encapsulation protocol. It is a point-to-point encapsulation protocol. It actually runs right on top of IP, specifically protocol 47. We'll see that in a Wireshark capture a little bit later on. The tunnel, the GRE tunnel, provides us a way to transport protocols that the underlying network might not support. Maybe it's a network infrastructure that doesn't support the protocol being used at all. Maybe it's a network infrastructure that can't route packets because there's no routing information because we're using private addressing. Or maybe it's an infrastructure that doesn't support the type of traffic that we want to send, which is typically going to be something like multicast or broadcast traffic. The most common use case for any kind of tunneling is to connect remote locations that are geographically separated sites over some sort of public infrastructure. And the most common public infrastructure that we see is the internet. When we use this tunneling mechanism this way, the tunnel itself creates this, what we call a VPN overlay network between the different remote sites. Packets that are actually destined to the remote private networks get encapsulated inside of a new IP header that's then allows us to route over the public domain. Okay? We accomplish the tunnel configuration by creating something called a virtual network. You'll actually see it on the written exam referenced as an overlay network on top of a physical underlying infrastructure, which is the underlay network. All right. We have a logical interface that basically emulates a direct physical link between the two sites. That's what the yellow line in this particular topology is supposed to represent. So the tunnel interface encapsulates the original traffic, which we define as the passenger protocol. So let me actually put some of these definitions down here. The passenger protocol is my original traffic. That's what's going to get encapsulated using some sort of carrier protocol, which could be IPv6, it could be IPv4, whatever. So the carrier protocol is what carries the, we'll call it interesting traffic in this case. So these are definitely terms that you'll see on the test. The concept of a carrier protocol versus a passenger protocol. The carrier protocol then actually encapsulates the data inside the transport protocol. So we also have another element called the transport protocol. And the transport protocol is what we use to what we use to route. Over the transit domain. All right. So all kinds of terms that we see, and this is the underlying architecture. So you'll have data, if you will. Let me pull up a diagram here. You'll have some host, v6 or v4 host, that sits behind, that sits behind the network. Those are your network. So we got v4 and v6 packets. You got some perimeter router that's running the GRE encapsulation. And you've got maybe your v4 only network. I'll just put a little cloud in here. We'll call that the v4 service provider network. And then you've got some router over here. So this is a customer edge router. This is a customer edge router. And then you've got your v6 and v4 networks over here. All right. Now, as the data moves, and we'll take a look at this in Wireshark as well, but as the data moves across this network, you're going to have these encapsulations that are occurring. So you've got your v4 header, which is the outer header. That's going to be your transport protocol. All right, that's going to allow us to route across this network. All right, you've got the carrier protocol. I'll put a CP for carrier protocol. In this case, the carrier protocol could be GRE, but it could be IP and IP, perhaps. We'll take a look at that at the end. And then you've got your passenger protocol. All right, in this case, we'll just call it V6. So we're taking this V6 traffic, sending it across the network. That's supposed to be a number 4 there. This is what allows us to route across the domain. And then, of course, once I get to the other side, all that information is going to be pulled back or pulled off, right? So that we can eventually get back to where we need to go on the receiving side. So that's what tunneling is basically allows us to do. The traffic that enters the tunnel is going to get forwarded. It's going to get hidden from the underlying infrastructure. It gets received on the other end, and then it gets unwrapped at the other end for further processing. Now, the devices in the transit network don't actually examine all of the original IP packet content, but one of the things that I do want to point out here is that we do not have, in this case, encryption. Tunneling protocols, by default, do not provide for the CIA process, right? Any kind of security class, you learn all about that. Confidentiality, integrity, or availability. So we might add other functions to this process. Other functions might include encryption. Somebody just dropped off the WebEx. Who did we lose? Let me see. Nope, everybody's still there. That's weird. Okay. So we might add other functions to incorporate these pieces, but that's a discussion that we're going to have later on when we start to get into things like DMVPN. All right. There are many different types of carrier protocols. We could do L2TP, IP and IP. Different carrier protocols include L2TP, IP and IP. We'll take a look at that one. And GRE. And there's others, right? These are just some of the common ones that we see. But the focus of our discussion today in this lesson is to focus on GRE and our IP and IP configuration. Okay? So the GRE tunnel provides an interface. that we forward the data. The data in the sense of this case is what we call the passenger protocol itself, which could be V4 or V6. And then the tunnels have those three components. You've got the delivery header, which is your transport protocol. You've got the GRE header, which is your carrier protocol. And then you've got your payload packet, which is your passenger protocol. So this is the, we'll call this the payload packet, just to be, so you guys can remember this later. The carrier protocol in our case is going to be either GRE or IP in IP. And then the payload, the transport protocol is the delivery header, which is what the data is being actually encapsulated inside of as we move to the other side. All right. The passenger protocol itself is actually going to be sent to a Gre Tunnel Interface, which we have to create, and that's part of our configuration today. We're going to take a look at that Gre Tunnel Interface. It's going to encapsulate the data using a GRE header, and then the packet that results from that then gets encapsulated into the transport protocol, which adds the delivery header, which is what we use to cross the underlying network. So let's say, for example, in our case, and we're not going to do IPv6 in this case because it doesn't really change anything. I mean, I guess we could add IPv6. Yeah, what the heck? We'll add IPv6 to this process. Let's say our our passenger protocol is IPv6, but we want to tunnel that across the V4 architecture. The device that's going to be forwarding the V6 packets sends the packet to the GRE tunnel. And then the Gre Tunnel Interface adds the header that it uses as part of the IPv4 protocol stack to deliver it across the underlying IPv4 network infrastructure. GRE can actually be used with lots of different combinations of passenger protocols. When we're doing our config, I'll show you some of the question marks that show that. But IPv4 and IPv6 are usually the most common. So we can take GRE and we can use IPv4 as the transport protocol to tunnel V4. That would be like if we're going to have some sort of private addressing scenario. We can take IPv4 as the transport protocol and tunnel IPv6. Very similar to like a 6-to-4 type of tunneling scenario. We can make IPv6 as the transport and tunnel IPv4 if the carrier network is IPv6 only and the tunnel and the passenger protocol is V4. Or we can do IPv6 and IPv6. All right. Why do we use these GRE tunnels? Because we like to be able to support multiple protocols and packet types across lots and lots of different transport networks, especially like the internet. All right. Also, a lot of times, and you guys have probably done this many times, being that you're in the CCIE level, you've probably configured GRE many times, but a lot of times when it comes to routing, hello packets and updates and queries and replies and other types of even OSPF packet types, we're going to be using multicast as the protocol, and maybe the WAN does not support that multicast traffic. So the multicast hello packets go out the interfaces, but because that multicast traffic is unsupported over the public transport, we have to set up the tunnel. All right. So that's basically what the concept is. And we've got our topology here where we're going to go ahead and essentially set that up. So let me talk a little bit about the topology. All right. I think I just clicked on the wrong button there. Let's go ahead and talk about the topology. Get rid of that. So I've got PC1 on the left with an IP address of 10.10.10.10. And I've got PC2 on the right with an IP address of 10.10.11.10. So clearly, two different RFC 1918 address spaces. The internet here is just a router in between that's simulating, connectivity between the branch and the HQ location. We don't have multiple hops, but there is no direct reachability between PC1 and PC2. The gateway of PC1 is this router. The gateway of this PC is this router. And we have essentially just connected routes here. There's a default route here that points up to here. There's a default route here that points up to here, but the internet is completely unaware of those PCs themselves. So if I were to go into PC number 2 and I was to try to ping PC1, it would fail. 10.10.10.1, well, we'll go 10.10.10.10. So the ping is going to fail, but the ping is definitely going out to the internet. And I'll talk a little bit about the network layer reachability stuff that we have to confirm before we can actually go in and configure and verify our GRE operations. Again, this is not, we're not adding encryption, we're not adding anything else to this. We're basically trying to do basic GRE configuration. We're going to look at multi-point GRE over IPsec later on when we get into the configuration of DMVPN and so on. All right. So the first step in this configuration is to go ahead and create our tunnel interface. Let me do a show IP interface brief just to make sure we don't have anything configured. So I'm going to go config T, interface, tunnel, and I can create any number I want. Let's go ahead and just do 80. All right. And I have some options that I can configure with this tunnel interface. Quite a few options, actually. We're not going to get into all of the details of all the different options that we can specify. There's a lot, right? When we get into some of the other technologies later on, we'll, of course, look at some of the other concepts later on. But for now, we're just doing basic GRE tunneling. So there's two things that we have to do when we define the tunnel. So we create the tunnel interface. One, create the tunnel interface. And that would be in global config mode. Interface, tunnel, whatever the number is. So we did 80 in this case. And you'll notice that I'm now in config-if. So the next thing that I have to do is I now have to specify the tunnel source and the tunnel destination of the traffic. Now, if I look at the diagram here, the tunnel source is going to be this interface here, serial 20. Remember, this is where we're establishing the tunnel between the two routers. So the tunnel source I can specify as this IP address. The tunnel destination I'll specify as this IP address, or I can use an exit interface. Keep in mind that most likely we'd want to use an IP address just to make sure that it's consistent. We need to specify our tunnel source and destination. Really simple. We're going to go ahead and specify the tunnel source as this address here. So we simply come in here and say tunnel source. We can specify an interface. We can also reference another tunnel if we want to. We can reference a serial interface. Lots and lots of different options. VLAN, V6 address, V4 address, and so on. Oops, didn't want that. I want to reference this IP address. One of the things that you should probably do, quite frankly, is test your underlying network layer reachability first. Because if you're specifying the tunnel source and tunnel destination and you haven't verified that you have reachability between the tunnel source and tunnel destination, then that's not really going to do you any good. So I'm going to do a quick ping to 209.165.200.241. And I can definitely ping the destination so you can see that the tunnel interface came up and the tunnel's active. The only reason this tunnel interface comes up is because of the recursion, the route recursion that we were able to do locally on the router. If for some reason in this topology I shut this interface down on the branch side, the tunnel interface would still stay up because of the local network layer or the link status of the local connection, and because we have a default route that points to that link, so the route recursion would work. So that's something to keep in mind. Just because the tunnel is active does not mean that the tunnel is working. So always do a ping or whatnot to go ahead and test to see if you have the appropriate reachability, right? So if I do a show IP route, my point is here that because I have a default route, I don't have a route to 209.165 on this router, but because I have a default route, the local router believes that it can reach that destination. Okay. Now the underlying protocol could be a dynamic process, it could be an MPLS backbone or whatever, but always make sure you have that network layer reachability before you specify the tunnel source and tunnel destination. Now the next thing that we have to do is we have to identify what the payload protocol is. It could be IP, it could be IPv6, it could be CLNS, for example, if we're trying to route ISIS over the tunnel. The key is that the generic encapsulation that we're using allows us to carry anything over this particular tunnel. Optionally, you can also configure keep alives as well, because there's nothing here to indicate that the tunnel is actually active, because Ken keeps losing his connectivity. Let me see. He sent a Slack message here. Let me see what that says. Okay, he says he's missed half the class because he keeps losing his internet connection. Okay. Well, that's what the videos are for. So anyway, we can take a look at setting up a keep alive mechanism. I'm adding the keep alive feature to make sure that we can identify whether or not the tunnel is actually truly active and reachable, as opposed to just relying on the local route recursion lookup and whatnot. All right, but the idea here is that I can put anything inside of this tunnel because it is GRE. Well, it's not GRE yet. Actually, it is, because if I do a show interface, tunnel 80, you can actually see that the encapsulation mode is tunnel, and the default tunnel protocol and default tunnel transport is GRE with IP. So if I don't specify a tunnel protocol, and if I don't specify the tunnel transport, which I haven't because I haven't even put an address on the interface yet, it essentially allows us to carry this information. So now I need to put an IP address on the tunnel interface. If I did an IPv6 address, I could do that as well. That means that the transport protocol would most likely be IPv6. And in our case, the transport is IPv4. All right, so I'm going to create an IP address on this. I'm just going to do 80.0.0.1, 255.255.255.0. And I'm going to go into my branch location and essentially duplicate that configuration. Interface tunnel 80, tunnel source. Let's get the IP off of our diagram here. And tunnel destination. And get the IP off of our diagram here. And we'll put an IP address on here of 80.0.0.2, 255.255.255.0. By the way, I used public addresses in this case, but most likely you wouldn't. You would just use some sort of private addressing that when they're on a common subnet. So if I ping 80.0.0.1, I can see that I can actually ping the tunnel destination, which is good. That's the second check that we're going to go ahead and put into our configuration. So we specify the tunnel source, 1.1.1.1, and we specify the tunnel destination. Of 2.2.2.2, and we then put an IP address on the interface. IP address 209.65.200.241 or whatever it is. All right. This is tunnel interface on R1, and we would do the same thing for tunnel interface on R2. And the only thing here would be that these addresses would swap. And this might be 198.56.100.10, whatever. All right, make sure you can ping make sure you have reachability between the public IPs, regardless of the transport. So whether it's a static or default or dynamic or whatever. And then also make sure you can ping between the tunnel interfaces. Remember, the default encapsulation or the default tunnel mode for Cisco is GRE with IP. All right, GRE being the tunneling protocol and IP being the transport protocol. The passenger protocol is whatever we're putting inside of it, and then the carrier protocol is going to be GRE, and then the transport protocol is going to be IP by default. Okay. Now, what if I did want to change that? I could change that by saying, let's say I wanted to say IP. Let me see. No, let me see. IP. Let me hold on one second. I lost my train of thought completely here. Tunnel mode. There we go. I don't know why I didn't think of that, but tunnel mode. Yes. So other than GRE, we can specify other tunneling protocols. We could tunnel over MPLS, tunnel over IPv6, lots and lots of different options. Well, when we do our DMVPN configuration, you'll see that we're going to use different options as well. So I can do GRE. This would be a little bit redundant unless, for example, my transport protocol is going to be IPv6. So I want to encapsulate GRE with IPv6 as opposed to, so if I do a show interface tunnel 80 now, you'll see that my tunnel is still up and active, but the tunnel line protocol is down because we don't have IPv6 enabled. But you can see that the tunneling protocol is GRE, but the transport is IPv6. All right. So if I show run interface tunnel 80, you can see that we have our basic configuration here. All right. So does that mean now we should be able to ping between our destinations? The answer is no, but let's go ahead and give it a shot. So ping 10.10.10.10. Ah, it did work. All right. So I wasn't expecting actually the ping to go through, but let's walk through the scenario here. So I do a show IP route on our branch router here. I've got the 10.10.11 subnet. And I've got the default route. So actually it does make sense because what's happening in this case is that the traffic is hitting the branch router. The 10.10.10 subnet is not included in my routing table, but it's going to match the default route. And that default route points out this interface. This is interesting. Let me look at my topology diagram here, because if you follow the logic here, this traffic is going to match. Obviously, this guy's going to have a gateway to go to the branch router. That traffic is going to match the default route to go out. But what's telling it to actually go to the tunnel interface? Because that's not something that should happen in this case. Let me do a capture real quick and see if we're actually seeing the traffic being actually encapsulated inside of GRE. Because there has to be a way to associate the type of traffic that you want to a tunnel interface. And what I was going to do was I was going to go ahead and add EIGRP to our topology and include the tunnel interface as well as our Ethernet interfaces in EIGRP, so we could establish an EIGRP relationship across the tunnel and dynamically share network reachability information. But I'm very curious to see, maybe it's just a basic routing concept. We've got some, I don't have any default routes on the internet router, so the packet should be lost at that point. So let's see what happens here. All right, let's get rid of this, apply filter, not selected. Let's also get rid of CDP, apply filter, also not selected. All right, so let's do our ping again and see what we see here. All right, so we're not seeing anything here. Let me try something else here. Let me do a trace route. Oh, well, I'm such an idiot. You guys should have caught this. I'm pinging myself. Oh, no, I'm not. I'm pinging the other side. Yes, I'm pinging myself. Duh. I'm on, I thought I was in PC2. It's going to work if you ping yourself, by the way. Let's try that again. And let's ping 10.10.11.10. There we go. That's exactly what should be happening, because I haven't really tied the destination network to anything. Yeah, it's going out the default route and it's getting to the internet router, but because it's not being encapsulated, the internet router is simply rejecting the data because it doesn't know where the 10 network exists. So even though the tunnel is up and we've got reachability between the tunnel endpoints, we're not actually seeing any traffic being encapsulated. All right. So obviously that's our next step. So we're going to use router EIGRP1 in this case. I'm going to go ahead and specify a network of 10.0.0.0. And I also want to include the tunnel interface as part of the EIGRP process. So I'm going to be running EIGRP on the tunnel interface and my local, dang it, wrong router. No router, EIGRP1. And let's go to HQ, router EIGRP1, network 10.0.0.0 and network 80.0.0.0. Now, if I do this on the branch router, oops, what we should see here is that we should get an adjacency come up between the two endpoints. Router EIGRP1, we need to make sure we're running the same autonomous system number. Network 10.0.0.0 for the LAN, and network 80.0.0.0. So what should happen is I should now start to see hello packets being encapsulated inside of my GRE and my transport protocol. Yep, I just got an adjacency. If I go back here, we can see now the hello packets are being generated. Notice the source and the destination. Now the question is, how are those being generated locally and what's happening when they get sent out? So if I open up one of these packets, we can actually see that the packet is being encapsulated inside of GRE. Here is our HDLC frame. The protocol is IP. The protocol field here references GRE. And you can see the tunnel source and tunnel destination. So this is, when it comes to our notes here, this is my transport protocol header. Let me use this diagram here. So that's the transport protocol header. Then we're going to see the GRE header, and then we're going to see the actual passenger protocol. So here is my GRE header, and the protocol type is IP, so we don't really have too much in the GRE header. It's a pretty straightforward header. We've got 16 bits of flags inversion, and then we've got 2 bytes of IP. So we're talking about 32 bits of overhead, or 4 bytes of overhead, excuse me. Yeah, 4 bytes of overhead. And then we have our actual payload, our what we defined here as our passenger protocol. And so the carrier protocol is GRE, and the passenger protocol is our EIGRP packet. So if you look at the source and destination IP here, the source is the tunnel interface. The destination IP is our EIGRP multicast group address. And we can see that the protocol ID is 88. So that's our EIGRP packet, hello packet. So it's a really, really simple concept. Obviously, now that we have routing, if I do a show IP route, I should actually see the 10.10.10 subnet is tied to the GRE tunnel interface. And if I ping 10.10, let me go up from the PC. If I ping 10.10.10.10, it now works. All right? It's a really, really straightforward concept. We could add other things. We'll talk about some of the other concepts that we'll add to this later on when we get into some of the more details with DMVPN and some other tunneling techniques that we would apply in a more complex environment. But it's a really basic concept. Now, what about IP and IP tunneling? Right? Now, there are some pluses and minuses to IP and IP tunneling. It is also a point-to-point protocol. The configuration is almost identical to what we just saw, but unlike GRE, we use a different protocol number. We'll continue with our capture here. And it is not multi-protocol capable. So we can't configure things, we can't carry things like IPv6, we can't carry CLNS. But let's take a look at what the CLI configuration looks like. We'll do some captures on our data plane. We're already got the capture running anyway, but I'm going to show you potentially how you could do a capture with a PCAP application within CLI. I'm not going to complete the whole config, but I'll show you how you might be able to do some packet captures. I doubt you'll have to do any packet captures on the lab. That level of troubleshooting is probably not required, but it is still kind of cool to know. All right. So let's go ahead and switch this over to IP and IP. Just like always, we configure this between our HQ and branch. We make sure the routers have reachability. We talked about that. Specify our tunnel source, specify our tunnel destination. But the only difference here now is that we are going to identify the carrier protocol. All right. So in the case of tunnel mode, instead of saying tunnel mode GRE IP, we're going to come into the router and we're going to say tunnel mode IP. So interface tunnel 80, tunnel mode IP, and on the branch router, interface tunnel 80, tunnel mode IP. All right. If I do a show interface tunnel 80, we can see that the tunnel is up, it's operational. Notice the bandwidth and delay of the tunnel too. That's actually really important to note. The bandwidth is only 100 kilobits a second, and the delay is 50,000 microseconds. That's more than twice what a serial interface might have. So if you are using a tunnel as an alternate path in a dynamic process like OSPF or EIGRP, just be very aware that the tunnel interface has pretty substandard values when it comes to routing. You may have to manipulate some of those values to get a better routing, out of the over the tunnel or whatever it might be. Just something to keep in mind. A lot of people are not actually aware, that's that's such a those are such poor values. Okay, so if we go back to do our Wireshark capture, we should still be seeing those hello packets. Those go out every 5 seconds. So we're still seeing the hello packets. If I go in now and I look at the packet, you can see that the protocol now is protocol number 4, which is IP and IP. We don't actually have a GRE header in this case. It's literally IP carried inside of IP. So this is the outside IP header, this is the inside IP header, and then we have our EIGRP payload. This is kind of more open standard as far as being able to be supported on lots and lots of different platforms. So if you're only concerned about carrying IP, that's all you need to worry about. All right. So I guess that's about it. Oh, I was going to show you guys real quick. I thought I would go ahead and, even though we're doing packet captures in Wireshark here directly through GNS3, I thought I would show you guys how you might be able to do a similar packet capture on a router using the CLI packet capture feature. Again, we don't have actual flash, so we can't really store the files, but we want to create a PCAP on the data plane. So the first thing I would do is I would do a monitor config t, monitor capture. Is it even going to let me do it? It's not going to let me do it. Yeah. Well, basically, I'll run through the syntax. It's going to be errors here, but I would do a monitor capture 1, and I could say match whatever protocols I want to match. In this case, I would just match any protocols. Oops, I would spell it right, of course. It's still not going to work, but let me spell it right anyway. Monitor capture 1, match any. And then what I would do is I would do a interface. So I could say monitor capture interface, in this case serial 20, and I can say capture traffic in both directions. And then I start the capture, monitor capture 1 start. And what it's going to do is it's going to start to capture that information to your flash, all right? Or to your memory, I should say. And then you have to export that file using TFTP to an external destination. So you could do, say, for example, I don't think this will work either. Show monitor capture 1 buffer. Huh. Maybe the syntax is just slightly different here. Let me try something else here. Monitor capture. So it looks like it's just a syntax issue. Event trace. Yeah. So maybe just I'm using legacy syntax here. I'm not sure what it is in here, but in any event, you would be able to capture that information. Then you can export that capture to a TFTP server, so you can look into the payload and whatnot. I doubt you'll have to do that on the lab, because if you're doing that kind of level of troubleshooting, you're most likely going down the wrong path anyway. All right. So the only other issue that would potentially come up is if you're going to have recursive routing errors within the tunnel itself. So let's say, for example, I don't know if I can recreate this. Well, let me kind of describe what it is, and then we'll just leave it at that. It has to do with how the recursive routing works, right? The criteria to install a route in a table is based on the final interface that the packet needs to go out of. Because the tunnel is the outgoing interface, we want to make sure that that destination is going to be based on reachability to that tunnel destination. There is no protection mechanism to prevent from creating a routing loop in this case. So the tunnel destination should never recurse to itself. So the tunnel destination should not point to the tunnel itself. Once that happens, then you're going to get a route recursion or a routing loop, and the tunnel actually should go down. Let me see if I can... I mean, you would never do this, but let me see if I can at least show you what it looks like. So I could do IP route Actually do a show run. All right, so IP route 209 dot, no, let me do 195.200.145.0.255.255.255.0 tunnel 80. Yeah, there we go. So what's happening here is that we've got essentially, like you would never do this, but you've got a static route that points essentially to the tunnel interface. So this is where the tunnel destination is. It should not point to the tunnel interface. It should point to some sort of external network, right? And you can see here, as soon as that happened, we have a loop in the tunnel, and the tunnel gets temporarily disabled due to that recursive routing process. So if you ever see that, just make sure that the underlying protocol is never commingled with your overlay protocol. We see this potentially if you have a scenario where you're running EIGRP on the outside, but you're also running EIGRP on the inside, and they're part of the same autonomous system number. That would not be a good thing. That's where you're going to get that route recursion problem. All right. It also could be could happen if you have some maybe metric problems or administrative distance problems. In our case, we're using a static underlying protocol, the default route, to resolve the tunnel destination, and we're using EIGRP as our overlay protocol, right? So just something to keep in mind. All right. Well, took a little bit longer than I thought it would, but I think we're all wrapped up for today. That was a very basic discussion about GRE tunneling and IP tunneling. Later on, like I said, we'll get into a lot more details. So we'll wrap up this video, and we'll see you guys in the